Hello everyone. In this lecture, I will continue introducing the procedures in making cladograms. I will first introduce a less commonly used method, the phonetic method, and then introduce the parsimony and consensus principles, by which we compare and make choice of the trees we obtain. The phonetic method is based on dissimilarity between the taxa we study. Usually, a dissimilarity matrix between the taxa are needed. It can be applied to both discrete and continuous datasets. However, the phonetic method has its weakness. First, if you are dealing with taxonomically remote species, sometimes it would be difficult to find homologous characters for comparison. And in other cases, the states of the homologous characters found are seriously affected by convergent evolution. This is partly because of lack of polarization of the continuous characters used in this method. Also, the phonetic method assumes that the rate of evolution is constant. However, this is not often the case. Again, let's use the Austrocode dataset as an example. In the last lecture, this dataset had been used for Wagner algorithm. It contains 25 characters coded for each of the 4 Austrocode species. In order to apply the phonetic method, which employs a least similarity joining here, we first calculate the dissimilarity between every 2 species. Then, with these dissimilarity values, we have this dissimilarity matrix. We will apply a phonetic method to reconstruct the phonetic relationship between these Austrocodes. First, we find the smallest dissimilarity, that is 12%, between Cyperidopsis video and Potamocypris variegata. We connect the 2 species together as part of the cladogram. Then, we need to join the 2 species together and treat them as a single element in the following analysis. We do this by averaging the dissimilarity values of these 2 species to every other species, in this case, only to Iliocypris mongolica and Heterocypris incongruens, respectively. Now, we have finished the joining and obtain a new matrix. In this matrix, again, we find the smallest dissimilarity, that is 26%, between Heterocypris incongruens and the joined element. We then connect Heterocypris incongruens to the joined element as part of the cladogram, and then join them in the matrix to form a new, bigger element. Again, this is done by averaging the dissimilarity values. Now we have obtained a new matrix. There is only one dissimilarity value between Iliocypris mongolica and the joined element. Then we connect the 2 together and finish the clustering. If there are more taxa, repeat the above steps, and every time join the 2 elements with the smallest dissimilarity value together. We can see that the topology of the cladogram we build up is the same as the one we made using Wagner algorithm, but please remember the weakness of the phonetic method I mentioned earlier in this lecture, and use it with caution. The parsimony principle is based on the hypothesis that during evolution, the characters of a lineage should evolve as few as possible, and as a result, the cladogram with the smallest number of character changes should be the preferred solution. Therefore, if we have a number of cladograms derived from the same dataset, we should select the one with the shortest length. And how to measure the length of a cladogram? It is measured by the total steps of the changes of all the characters along the cladogram. Suppose we have the following dataset, and we have made a cladogram based on it. Then, how many times have the characters evolved? Because each node in the cladogram represents a speciation event, for each of the nodes there is a character change. So, the characters X, Y, and Z would have changed at the corresponding branching points, and the total number of character changes is 3. This is the tree length. We can show the changes of every character separately. This is the shape character. This is the color character. This is the size character. Every character has changed once, so the total number of changes is 3. In practice, there are 2 types of commonly used parsimony methods: Wagner parsimony and Fitch parsimony. They are used for ordered and unordered character states, respectively. The 2 methods produce the same result for binary characters, but different results for multi-state characters. For example, we have the character X coded in 5 species, and we have a cladogram for them based on a number of characters. If we think X is an ordered character, that is, its state can only change between 0 and 1, between 1 and 2, and between 2 and 3, but can't change from 0 to 2 or 3, and so on. Then, we apply Wagner parsimony to calculate the number of changes of X at every node. And the total step is 4. By contrast, if we think X is an unordered character and can change from one state to any other state, then we use Fitch parsimony. It has a different algorithm to calculate the change at every node, and the total step is 3. We can see that the 2 methods return different tree lengths. In practice, we may use different parsimony methods for different characters, and the tree length is the sum of the changes of all the characters. Consensus is the method to combine different trees together. Suppose you have more than 1 trees made by different methods, or with different datasets, and that the topologies of these trees are not completely the same. Then you will need to combine them together to form a single explanation of the evolutionary history. This is done by retaining the common topologies and removing some of the conflicting topologies. There are a number of consensus methods. Among them, there are 2 commonly used ones. The most commonly used one is strict consensus. It retains monophyletic groups that appear in all of the cladograms. The second one is the majority rule consensus. It retains monophyletic groups that appear in certain amount of the cladograms, this amount being between 50% and 100%. As an example, we have 5 trees generated for the taxa A, B, C, D, E, and F. These trees are identical with respect to the E and F parts, or that they all contain the monophyletic groups ABCD, ABCDE, and ABCDEF, but are not all the same for the rest part. For the monophyletic group ABC, it appears in the left 3 trees, but not in the right 2 trees. For the monophyletic group ABD, it appears in the right 2 trees, but not in the rest 3 ones. The monophyletic group ABCD appears in all the cladograms. As a result, if we apply a strict consensus, we can only retain the monophyletic group ABCD and the identical parts of the trees. In fact, by doing this, we also retain the monophyletic groups ABCDE and ABCDEF, which appear in all the 5 trees. And we have to leave the internal relationship of ABCD unresolved. And if we apply a 50% majority rule consensus, then in addition to the monophyletic groups ABCD, ABCDE, and ABCDEF, we can also retain the monophyletic group ABC, which appears in 60% of the trees. In this lecture, we have learned a less frequently used method to build cladograms, the phonetic method. It can be applied to both discrete and continuous data. It assumes that the rate of evolution is constant. Please remember it has serious weakness, and please use it with caution. In order to select the best tree, we need to find the shortest one. For calculating the number of changes of a character, we have different methods. For example, the Wagner parsimony and the Fitch parsimony. In practice, they can be used in a mixed way for different characters. And in order to synthesize different trees, we need to do consensus. For example, strict consensus or majority rule consensus. As a brief summary of my lectures, please know that they are a very incomplete, superficial introduction to cladistics. In order to learn more, please read more references. Although we have shown some examples of making cladograms, in fact, today people do not usually do cladistics by themselves, but we use the computer because the numbers of characters and species we meet are usually large. However, before inputting the data into the computer, the researcher needs to code the morphological information into the matrix, and the quality of this matrix will significantly affect the cladistic result. And the study of the chapter can help you do this better. Also, by learning about the basic principles of cladistics, you will be able to have a better understanding of various cladograms you read of in the literature. Okay, that's all for my lectures. Thank you.